All right, so this video is just going to be me working out random problems involving the electric field, involving voltage or potential, and involving force, Coulomb's law, anything that we've covered in this unit so far. So I'm just going to be making up problems on the spot, so forgive me if they don't turn out to be exactly all that great. But here we go. So we have yeah, we'll call them protons. We have a proton here, and we got a proton here, and they are really, really close to each other. They are at a distance of, let's say, half a millimeter. All right, half a millimeter. So we know we have a charge here, and we have a charge here. And the question is, what is the net force, or just regular force, because we only have one here. What is the force on the charge on the right? So we have two protons. Well, what's the charge on the proton? Well, the charge on the proton is exactly the same as the charge on the electron. It's just positive. So it's 1.6 times 10 to the negative 19th coulombs. So when you stick that into Coulomb's equation, Coulomb's law, then we get K Q1 Q2 divided by the distance squared. So that's going to be 9 times 10 to the ninth, then multiplied by 1.6 times 10 to the negative 19th, and we got two of those, so I'm just going to square that, and we divide that by half a millimeter. So that's 0.5 times 10 to the negative 3. Put it in scientific notation. We could have just moved it 3 decimal places to the left, so it would have been 0.0005, but I like this better. So, and we need to make sure that we square that. So when you stick it into your calculator, and let me calculate this real quick. We get a total force of 9.2 times 10 to the negative 22nd newtons. Now, this is a little bit smaller, right, than what you guys might be used to in calculating in class, but we're also talking about two very small charges, and even though they are really close to each other, the force on them is still incredibly small. Now, if you think about this in terms of the mass of the proton, is something like times 10 to the negative 27 kilograms. So you still actually have quite a bit of force on the proton with them being that close to each other. Well, now that we have a proton, we have the force over here, we could calculate how much energy is here. So if we want to figure out how much potential energy is between these two particles, then we can use the potential energy equation, also known as the work equation, and that's K Q1 Q2 divided by R. So notice how they're different. This is R squared, this is R. This is the basically to get from here to here, you had to multiply that by a distance. Well, that makes sense, right? Work is equal to force times distance. That's where we got this equation from. So putting that in, 9 times 10 to the ninth, 1.6 times 10 to the negative 19th. There's two of them still, and we're going to divide it. Now, in this case, it's just going to be divided by R. And we're going to get, again, let me calculate. And we're going to get 4.6 times 10 to the negative 25 joules of energy. Again, doesn't really seem like a whole lot, but taking into account the fact that these are really, really small particles, this is actually quite a bit of energy. Okay, so now this is what we can do if we have multiple charges involved. We can figure out the force between them, we can figure out the actual potential energy harbored in them, but we cannot do anything that involves um, the electric field or anything that involves voltage, mainly because of the fact that that the electric field and the voltage or the potential only depend on one charge at a time. So if we continue on about our business of this calculation, we can take this down and go, okay, we only have one proton. Okay, one proton, and we have a distance somewhere over here that let's say, is, I don't know, 2 millimeters away. And my first question is, what is the electric field at that particular position? Well, we kind of need to know what direction the electric field is. The electric field is still a vector, so we need to know what direction the electric field is going to be. Well, this should be relatively simple at this point because we know that the proton is a positive charge and the electric field just goes out in all directions from the proton or the positive charge. So therefore, at this point where the x is, the electric field is going to be to the right. Okay, it's going away from the positive charge. Well, can we calculate how big the electric field is? Yeah, of course we can. We can say the electric field is equal to kq divided by r squared. Okay, I had to remember for a second if it was r or r squared. So this is the electric field equation, and this is going to be what you deal with when you deal with a charge like this. So plugging in numbers, we have 9 times 10 to the ninth. We have the charge, 1.6 times 10 to the negative 19th. We divide it by 2 millimeters squared, 0.002 squared, and then we do the calculation. And we get something that says it is 3.6 times 10 to the negative fourth newtons per coulomb. Okay, now some of the other problems that we've had in class had an electric field that was really, really big. I think some of the other ones on the review was something like 32,000 or 16,000 or something like that. But if you have to recall that this is a really small charge. Proton is a really small charge. It's not on the order of micro like what we have been dealing with. It's just a really small charge times 10 to the negative 19th. So this is still quite a bit of force here when we're dealing with a single coulomb of charge. Remember, a coulomb of charge is really, really big. So what I'm just trying to show is that this is a reasonable answer. You always want to take a look at your answer and say, is it reasonable? Well, now that we have the electric field, we might be able to take a look at the voltage. How much energy per unit charge do we have here? Well, that's the other equation, kq divided by r. And putting all that together, we have 9 times 10 to the ninth times 1.6 times 10 to the negative 19th. And we divide that by the single distance, 0.002. And sticking that in your calculator, we would get a voltage of 7.2 times 10 to the negative 7th, and this is volts. Volts, or you could do it as joules per coulomb, right? Remember, joules per coulomb is the same thing as volts. So there is the answer for how much voltage. Now, it might look like we were just throwing around numbers here. You know, we have two numbers associated with the same position, but one is a number that it talks about force. If I were to put a coulomb there, how much force would it feel? The other one is a scalar, and it talks about energy. How much energy would a coulomb of charge have if it were sitting right there? Okay, just keep going on, reviewing some of the concepts that we've had. Talk about electric fields from things like a positive and a negative charge. We know that it comes out of a positive charge and goes into a negative charge, and so you end up with something that looks like this. And you can have lots of different arrows coming out of the proton, or the positive charge, and we can have lots of different arrows coming in to the negative charge, and that's what it would look like. But if we had two positives sitting next to each other, they are repelling, and so their electric field lines diverge basically as they get towards the center and look very similar to this. And again, you can put as many as you want on there as long as you make sure they don't cross and that you're showing the right thing. There's basically an asymptote sitting right here that they don't cross, and that's right there, right at the midpoint between those two. And if you think about it, remember that we draw the electric fields like a positive charge, and if we were to put a positive charge right there, it would feel an equal amount of force on either side, and it would actually just sit there. It wouldn't move at all. Now, you put it up here, then it would actually shoot upward or downward, but that's not the same thing. All right, we keep going on. What if we have an electric field? What if I told you you had an electric field that was 25 newtons per coulomb, and I even gave you a drawing of it. Maybe I said that the electric field looks like it's doing this, which doesn't really look like anything that we've dealt with because they're parallel lines, but let's just say that it's a uniform electric field in all space, and it's 25 newtons per coulomb. And we stick a negative charge in this electric field, and we say that the charge is equal to a negative, I don't know, let's say 8 microcoulombs. Okay, so remember that microcoulombs, it means times 10 to the negative 6. Now here's my question: with what force is the negative charge going to feel? Well, we can take the electric field and multiply it by the charge, and that should give us a force, right? A coulomb multiplied by a newton per coulomb gives us a newton. So we can do that. We can have 25 newtons per coulomb multiplied by 8 times 10 to the negative 6 coulombs. And we get, again, let me calculate, and we get 2 times 10 to the negative 4th newtons. Now here's a question for you. What direction is that force? Well, the electric field is always drawn in the direction that a positive charge would move. So since we're dealing with a negative charge, then we basically have to turn around and say, oh, it's going to be the opposite. So this negative charge is going to go that direction. Okay, so the force is 2 times 10 to the negative 4th newtons to the left instead of the right. And you can almost visualize this uniform electric field being caused by a whole bunch of positive charge that was somewhere way over here. And if all this positive charge is here, this negative charge would want to get to it. All right, this will be the end of this video.